Hello again. Today we are going to work with systems of inequalities, which is our last lesson of the first semester of Algebra 1. All right, before we begin on actually getting into solving these by graphing, let's go ahead and do a little warm-up and make sure that we are good with determining whether or not we have an ordered pair that is a solution. So last time we figured out if an ordered pair was a solution to one inequality. Remember, if it's going to be a solution to the system, that means it needs to be true for not just one, but for both of our inequalities. So is 3, 5 a solution to the system? Well, what we would need to do is we would need to take our x and our y value and plug them in to both of our inequalities. So the first inequality, I'd rewrite 3, but then I'd replace x within 3, because this is telling me let x be 3, and then plus 5, and then I'd replace y with 5, and then I'm going to see, is that less than 34? Is that true or false? I would also need to take my ordered pair and plug it into the second inequality, which is going to give me 2, and then I replace my x with 3, and then minus 3. I replace my y with a 5, and then is that greater than or equal to negative 9? All right, so feel free to use Desmos, feel free to use a calculator to evaluate the left-hand sides of these. All right, so 3 times 3 is going to give me 9. 5 times 5 is going to give me 25. And 9 plus 25 is going to give me 34. For my second inequality, I get 2 times 3, which is 6. I get negative 3 times 5, which is negative 15. And then 6 minus 15 is negative 9. All right, so now I need to see if this is true for both. All right, so for my first inequality, I get 34 is less than 34. That is false. 34 is less than 34. That is false. They are equal, but this is not less than that. This is false, which means that this is not a solution to the system. Okay, just for the fun of it, let's see if it was true for the other one. Negative 9 is greater than or equal to negative 9. That one is true. Okay, but in order to be a solution to the system, it has to be true for both. And since it's not true for both, it means it's not a solution to the system. All right, so essentially we're going to be doing that, but instead of plugging these values in and only looking at one possible solution at a time, what we're going to do is we are going to take our two inequalities and we're going to get a graph, and we're going to see where do their solutions overlap, and then that on the graph, where are the shading overlaps, that's going to be where your solutions are for your system. So then you don't have to guess, you don't have to plug it in and check that way. You can just take any point from that shaded region and you have yourself a solution to the system. So this says identify 3 possible solutions to the system. Well, if I just pick any points from the shaded region, I have a solution. So for example, right here, it would be the ordered pair 4, 3. That would be a solution to the system. All right, any point from the shaded region. So right here, 3, 2, that would be a solution to this system. I don't have to take these ordered pairs and plug them in. I could if I wanted to verify, but all I'm doing is, since I already have this graph, I look to see in the graph where the solution lies. That solution lies in the shaded region. But not only that, okay, it also lies on any of the boundary line that's solid, that is adjacent to, that is hitting, that's touching the shaded region. So for example, right here, okay, this part of my boundary line would be a possible solution since it's solid and it's touching the shaded region. Same with right here. All right, so that means that this ordered pair right here, this corner point, since it was on 2 solid lines and it's touching the shaded region, that means that it would also be a possible solution. So another possible solution would be 1, 3. Points that would not be solutions would be anything from the non-shaded region, such as negative 3, positive 3. Negative 3, positive 3 would be right here. That's clearly not in the shaded region. 0, 0 would not be in the shaded region. But not only that, a point that is on the line but not touching the shaded region, okay, this one right here would not be a solution to the system. So that would be the ordered pair 0, 2. All right, so now we need to get the graph. So then somebody else could say, okay, this would be a possible solution, or this would not be a possible solution. So we need to get our graph, which means that we are going to graph not just one line, but 2 lines on the same coordinate plane. All right, so for this example, we have our 2 inequalities, and what I'm going to need to do is graph both of these inequalities on the same coordinate plane. So my first inequality is y is less than 3x. So that's already in the form y equals mx plus b, which is good news because now I can just go straight to identifying my slope and identifying the y-intercept. So the slope is the number directly in front of x, so in this case it would be positive 3, but I'm going to write that as a fraction as 3 over 1. And the y-intercept is what's directly after x. I don't see a number after x, which would mean that it would just be 0. So over here on the y-axis, I would find my point at 0. My y-intercept is my starting point, and then my slope tells me how to move. So this tells me I'd go up 3 to the right 1, up 3 to the right 1, up 3 to the right 1, or down 3 to the left 1, down 3 to the left 1, down 3 to the left 1. All right, then what I would do is I would look to see what type of an inequality symbol do I have, and in this case it's a less than, which means that this is going to be a dashed boundary line, that these points that I just graphed are not a part of the solution to this inequality. All right, so I'm going to go through and I'm going to make this so it's dashed. And there's a separate video that's going to help you directly with how to do this on Alex. All right, this is how I would be doing this by hand. All right, now what I'm going to do is I'm going to get my second inequality, which is y is greater than or equal to negative 4x plus 1. I'm going to compare this to y equals mx plus b, and it is also already solved for y, so I can go ahead and directly get my slope and my y-intercept. So the number in front of x is negative 4. I'm going to put that as a fraction as negative 4 over 1, and the b, the y-intercept, would be positive 1. So on my y-axis, I would find my point at positive 1, and then my slope tells me how to move, which is down 1, 2, 3, 4, and to the right by 1. Down 1, 2, 3, 4, and to the right by 1. Down 1, 2, 3. Oh, I ran out of room, so I'm going to go the other way now. So up 1, 2, 3, 4 to the left 1, and up 1, 2, 3, 4 to the left 1. Now, this one has an or equal to, which means I'm going to use a solid line because these points that I just plotted would be solutions for this inequality. So I'm going to use a solid line to connect these. All right, so now the goal is to figure out where's the solutions? Where does all of my shading overlap? All right, so I hope you notice that when 2 lines intersect, they intersect at a single point, and then they also create 4 regions to this graph, to this coordinate plane. All right, because they are creating what are called 4 angles, which you'll learn more about in your geometry days. So I'm going to put a big 1 over here. All right, so in this region, okay, where my solid green line and my dashed boundary line come together over here. Okay, this is going to be region 1. Up here we have a second region. Over here we have a third region. And down here we have a 4th region. All right, so what I'm going to do is I'm going to pick any ordered pair that I want, okay, because now comes the shading, which means test points. So I'm going to pick any ordered pair that I want as long as it is not on a boundary line. All right, so I'm going to pick any ordered pair that I want as long as it's not in a boundary line. That means I can pick this from region 1, region 2, region 3, or region 4. All right, so let's say I pick something from region 1. All right, so let me go ahead and just use this ordered pair, negative 2, 0. So here's my x, here's my y. So what I'm going to do is I'm going to plug it into my first inequality. So my first inequality was y is less than 3x. So I replace y with 0. I replace my x with negative 2, and this gives me that 0 is less than negative 6. Well, that's false. All right, so that means that this right here, region 1, it cannot be where my solutions lie. All right, so now what I'm going to do is I'm going to think about this. Okay, I just plugged this into my first inequality, which is y is less than 3x, which is the one that I did in this purplish pink color, the dashed boundary line. All right, so if region 1 can't be a solution, that means that region 2 also can't be where my solutions are because they're on the same line or on the same side as my dashed line. All right, so here's my dashed line. If region 1 can't be where the solutions lie, region 2 can't be either because they're on the same side as this dashed line. All right, so that means that my solutions either are in region 3 or region 4. So now I need to pick a new test point. So I need a new test point, and that's going to come from region 3 or region 4. It doesn't matter which one I pick. All right, so let's say I go for region 3. Let's say I choose the ordered pair 4, 4. All right, so now what I'm going to do is I'm going to plug this into my second inequality, which is y is greater than or equal to negative 4x plus 1. If I plug it into the first one, I already know it's going to be true, all right, because 4 is less than 3 times 4, 4 is less than 12. I already knew that one was true because I already did a test point for that one. I already figured out that I needed to shade to the right of this dashed boundary line. So now I need to plug this into my second inequality to figure out, am I going to shade to the right of this solid line or to the left of the solid line? Will it be in region 3 or will it be in region 4? So I'm using my new ordered pair, which comes from region 3, and I'm plugging it into my second inequality. And this is going to give me 4 is greater than or equal to negative 4. And then I replace x with 4 and then plus 1. So is 4 greater than or equal to negative 16 plus 1? Is 4 greater than or equal to negative 15? Well, yes, that one is true. Had it been false, region 4 is where I would have been shading, but since it was true, it means that region 3 is where my solutions lie. All right, so possible solutions. Okay, a possible solution to this one would be 4, 4. If I plug that back into both of my original inequalities, I get a true statement. Other possibilities would be any other point in this shaded region or any boundary line that's touching the shaded region that's on a solid line. So for example, this point right here, which would be at 2, negative 7, it would be a possible solution because it's on a solid boundary line that touches up against the shaded region. All right, not a solution would be any point from on this dashed line that touches the shaded region. So for example, the ordered pair 1, 3 is on a dashed it's on a dashed boundary line touching the shaded region. So it is not a solution because it's on that dashed boundary line. All right, let's go ahead and do another example. This will be our last example, but much of the same. All right, we have our two separate inequalities. So we have y is less than or equal to 1/2 x plus 2. So if I compare that to y equals mx plus b, I'm good to go because I already have y by itself on one side of the equal sign. So now I just compare. So the number in front of x is positive 1/2, which is telling me how to move. It's the slope. The number directly after x is positive 2. So that tells me the y-intercept. So on the y-axis, I'll plot a point at positive 2, and then the slope tells me how to move. I go up 1 to the right 2. I go up 1 to the right 2. I go up 1 to the right 2. I go up 1 to the right 2, up 1 to the right 2, or down 1 to the left 2. Down 1 to the left 2, down 1 to the left 2, down 1 to the left 2, and so on. This was an or equal to, which means that these ordered pairs that I just plotted are solutions to my first inequality, which means I need a solid boundary line. So I'm going to connect these points with a solid boundary line. All right, my next inequality is y plus 3 is greater than 3x. So y plus 3 is greater than 3x. When I compare this to y equals mx plus b, I don't have it yet. I don't have y all by itself. So that means that this positive 3 needs to move to the other side. Since going to the opposite side, I need to do opposite, which would be minus 3 on both sides. This gives me y is greater than 3x minus 3. So my m, my number in front of x, is positive 3, but if I write that as a fraction, that's 3 over 1. And my y-intercept, my b, would be at negative 3. The number directly after x would be that negative 3. So on the y-axis, I'm going to plot a point down at negative 3. And then I'm going to move 3 over 1. So that means up 1, 2, 3 to the right 1, up 1, 2, 3 to the right 1, up 1, 2, 3 to the right 1, up 1, 2, 3 to the right 1. Or down 1, 2, 3 to the left 1, down 1, 2, 3 to the left 1, right there. All right, and then I would connect these points with a dashed line. These points that I just plotted are not a part of my solution because it just says greater than. All right, so just because I'm working with a greater than symbol, which means that they're not a part of the solution, so I need to make a dashed line. Okay, so this is my boundary. We get as close to this as possible, but those are not actually included. All right, so once again, when two lines intersect, they intersect at a single point and they're creating 4 regions. All right, so I have my first region, my second region, my third, and my fourth. It doesn't matter which ones you label as what. All right, but we have these 4 regions. And the first thing that you're going to do is you're going to plug a test point into your first inequality. Any point that you want. We haven't done any test points yet, so any test point that you want as long as it is not on your boundary line. All right, so pick any test point that you want as long as it's not on the boundary line, and I think I'm going to go with 0, 0. All right, so if I plug this into my original inequality, I get 0 is less than or equal to 1/2 times 0 plus 2. So this is going to give me 0 is less than or equal to 1/2 times 0 is 0 plus 2. So is 0 less than or equal to 2? True or false? And that one is true. Had it been false, okay, I would have had to change my test point. But because it's true, it's telling me that region 1 is a possibility for where my solutions lie. Okay. Don't forget, okay, that this is my solid line that I'm comparing it to. So what other region is on the same side as the solid line? Okay, so look at the solid line, look at the regions. 1 and 4 are on the same side, which means that region 2 and region 3 are out. So that means that I'm either going to shade region 1 or region 4. So now what I'm going to do is I'm going to use the same test point in the second inequality. And again, the reason why I'm using the same test point is because it was true. So I'm going to continue working with the same test point. Up here, where I had my first one, which was false, I had to change test points. But on this one, where my first test point came out to be true, it means that this still could be where my solutions lie. So I'm going to use the same test point, and I'm going to plug it into my second inequality. So my second inequality was y plus 3 is greater than 3x. So I'm going to replace y with 0. I'm going to replace x with 0. And this gives me 0 plus 3, which is 3, is greater than 3 times 0, which is 0. So is 3 greater than 0 true or false? Well, that one's true. So that means that because it's true, it means that I'm going to be shading in region 1. All right, so possible solutions. Well, the test point that was true for both, 0, 0 would be a possible solution. Any other ordered pair that's in the shaded region would also be a solution. All right, 0, 2 would also be a solution because it is on a solid line that touches the shaded region. However, 0, negative 3 touches the shaded region, but it's on a dashed line, so that one would not be a solution. All right, and there you have it. That is how you graph systems of inequalities. Okay, to see if it's a solution for both, it has to be true for both inequalities. So the easiest way for us to tell us our solutions, where all of those lie, is to get the 2 lines that represent our boundary lines for our inequalities graphed, and then see where is that shaded region.